Tonight, we're going to explore something that seems ordinary and calm, but is actually one of the strangest realities on Earth. Time in the deep ocean. You've probably never thought about it. Scientists study it often when they measure currents, life, and geological changes underwater. But here's what most people don't realize. When you truly understand how time passes differently miles beneath the surface, when you grasp the slow rhythms and pressures of the deep sea, it changes how you see the world beneath the waves. This is not just about clocks or minutes. It's an environment so extreme and so hidden that even basic processes move in ways we can barely imagine. And by the end of this journey, you're going to understand exactly why time feels different in the deep ocean, how scientists study it, and why these hidden rhythms matter for life on Earth. Before we go any further, if you enjoy this kind of careful and deep exploration, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's dive in. The ocean covers more than 70% of the Earth's surface. Its waters stretch in vast, uninterrupted layers, sometimes shallow, often deep, and in many places, impossibly remote. From the coastline to the abyss, the ocean is not just a mass of water, but a complex system of pressure, temperature, and motion, all of which interact in subtle and precise ways. Near the surface, sunlight reaches in gentle rays, warming the water and supporting life that thrives in waves and currents. But as the ocean descends, light fades quickly. In the twilight zone, a few hundred meters below, shapes blur, colors vanish, and the world becomes muted. Beyond this layer lies the deep ocean, a realm where darkness dominates, pressure mounts, and temperature stabilizes near freezing. Here, the environment is constant in ways the surface never is. Movements of water are slow, changes are gradual, and time itself is experienced differently, both for living creatures and for the physical processes that unfold. Scientists studying these depths have often noticed that the world here behaves on slower scales. Sediments accumulate more gradually than in coastal regions. Chemical reactions proceed at a slower rate. Organisms grow more slowly, and lifespans stretch far beyond what is common near the surface. Even the flow of currents is measured in decades rather than days. At first glance, this slowness seems like a simple consequence of isolation. Yet, it is far more than a matter of distance from sunlight. The deep ocean exists under extraordinary pressures, caused by the weight of kilometers of water above. At a depth of 1,000 meters, pressure is about 100 times that of the air at the surface. Deeper still, near the ocean's floor, pressures can reach over 1,000 times surface pressure. These forces compress water slightly, alter molecular behavior, and influence the physics of how energy and matter move in this extreme environment. The temperature of the deep ocean is another key factor. While surface waters fluctuate with daily sunlight, seasonal heating, and weather systems, the deep layers remain near a constant 2 to 4 degrees Celsius. Cold slows the motion of molecules. In practical terms, this means chemical reactions, even those critical to life, proceed more slowly. Minerals dissolve at different rates. Organic matter decomposes gradually. In combination with high pressure, this low temperature creates a world where physical and biological processes unfold over longer timescales. A particle sinking from the surface may drift for months before reaching the seafloor, a journey that would be measured in hours in shallower waters. Microorganisms adjust their metabolisms to match these conditions, operating at a pace dictated by the stability of their surroundings rather than the rhythms of light and weather. Even the notion of time itself as measured by human instruments, can be subtly influenced by depth. While the differences are minuscule, they are measurable. Experiments with precise atomic clocks at various altitudes and depths show that time passes ever so slightly differently under the influence of gravity and pressure. In the ocean, the weight of the water column above affects how space-time behaves at a fundamental level. While these effects are not noticeable in everyday life, for scientific measurements they are real and must be accounted for when precision is required. The deep ocean is, in this sense, not only a physical environment, but a natural laboratory for observing the principles of physics under conditions rarely encountered on land. To reach the deep ocean is not easy. Human exploration requires robust engineering and careful planning. Submersibles must withstand pressures that would crush ordinary vessels. Sensors must operate reliably in cold and dark. Despite these challenges, researchers have gradually uncovered the character of the deep. Hydrothermal vents were discovered in the 1970s, revealing ecosystems powered not by sunlight, but by chemical energy from the Earth's interior. These vents host life that thrives in extreme conditions, organisms whose metabolic rates are slow and steady, shaped by the deep ocean's constant environment. Observing these ecosystems provides insight into how life adapts to extended timescales, showing that biological clocks operate on rhythms far removed from the surface world. Currents in the deep ocean also move differently. While surface waters can surge with storms, tides, and winds, the deep layers are guided by global circulation patterns driven by temperature and salinity. Thermohaline circulation, a vast conveyor belt spanning the oceans, carries water from the poles to the tropics over centuries. The movement is slow, almost imperceptible on human timescales. Chemical substances, heat, and even microplastics are transported with patience, accumulating effects over long periods. Scientists studying traces and isotopes find that elements released today may only reach distant regions decades later. In this way, the deep ocean is both a recorder and a slow conveyor of Earth's physical and chemical processes, where time seems to stretch in proportion to the scale and pressure of the environment. Biological life mirrors these slow rhythms. Deep-sea fish and invertebrates often live far longer than their surface counterparts. Deep corals grow millimeters each year, slowly building structures that can persist for centuries. Tube worms around hydrothermal vents may live for several decades, their metabolism tuned to a steady and predictable environment. These lifespans are a reflection of the broader slowness of the deep ocean. Where energy is limited, change is gradual, and the absence of light prevents the rapid cycles seen in surface ecosystems. Observing this life provides a window into a world where time does not dictate activity in the ways we are accustomed to, but instead shapes it in a measured, deliberate rhythm. Even the seafloor tells a story of slowed time. Sediment layers accumulate at rates of mere millimeters per year. Tiny particles of dust, minerals, and biological remains descend from above, forming layers that record centuries of environmental history. Microfossils embedded within these sediments provide scientists with precise data on past climates, ocean chemistry, and even catastrophic events. The deeper the water, the more gradual the deposition, offering a window into long-term processes that might be invisible in shallower regions. Each layer is a chapter, slowly written over decades and centuries, showing that time in the deep ocean is both patient and persistent, a stark contrast to the hurried rhythms of life and weather at the surface. The darkness of the deep ocean further emphasizes the separation from surface time. Sunlight penetrates only the upper layers, and below a few hundred meters, it vanishes entirely. In this perpetual twilight, visual cues for daily or seasonal cycles are absent. Organisms rely on other senses to navigate, feed, and reproduce. Many develop bioluminescence, producing light for communication or hunting, but these signals are local and limited. Without the sun's influence, cycles are longer, often aligned with the slow movement of currents or the availability of nutrients carried from above. Time, in this sense, is not measured by the rising and setting of the sun, but by the movement of particles, water, and energy through an environment that is inherently slow and stable. Even human perception is altered when submerged in these depths. Divers and researchers note that extended periods in submersibles or undersea habitats can feel as if days stretch and compress differently. While this is partly psychological, it also reflects the real slowness of environmental change. Currents drift without urgency, temperature remains steady, and the absence of sunlight removes natural cues that anchor human experience. Instruments record changes that are gradual and persistent, not abrupt or seasonal. Every observation, every measurement is a reminder that the deep ocean operates on its own scale, where time is less an instant-to-instant passage and more a continuum of slow, deliberate processes unfolding over years, decades, and centuries. The ocean is vast, but its depths are patient. Physical forces, chemical reactions, and life itself respond to conditions that are constant, extreme, and slow. Pressure compresses and shapes matter. Cold temperatures reduce the speed of molecular motion. Darkness removes cues for biological clocks. Currents move with measured persistence. Sediments accumulate layer by layer. All of these factors create a realm where time, while measured the same way as on land, feels stretched, elongated, and profoundly different. Scientists continue to study this environment, recording data that reveal the deep ocean's quiet persistence. Every measurement, every dive, and every sample adds to an understanding of a world where time is not hurried but deliberate, extending the rhythm of Earth's processes far beyond what humans usually perceive. Gravity is a force that holds everything on Earth, pulling objects toward the center of the planet. It is constant in daily life, so its effects seem ordinary. Yet gravity does more than keep our feet on the ground. It actually influences time itself. According to Einstein's theory of general relativity, time moves slightly differently in areas with different gravitational strength. The stronger the pull of gravity, the slower time passes relative to regions with weaker gravity. On the Earth's surface, these differences are extremely small, so humans cannot notice them. But when scientists measure time with precise instruments, even tiny variations become clear. The deep ocean, where water above creates additional weight, becomes a natural place to observe this effect. Here, gravity is subtly stronger than at the surface because of the mass of water pressing down, and that extra pull slightly slows the passage of time. Pressure in the ocean grows steadily as depth increases. For every 10 meters of water, pressure rises by about 1 atmosphere, roughly equivalent to the weight of the air at sea level. At 1,000 meters, pressure reaches around 100 atmospheres. At the deepest trenches, it can exceed 1,000 atmospheres. This immense force compresses water and other materials, squeezing molecules closer together. The physics of compression affects many processes, from the behavior of gases dissolved in water to the functioning of living cells. High pressure also alters the way materials absorb and transfer energy, influencing chemical reaction rates. While these effects are small in terms of everyday experience, over large scales of depth and time, they create measurable differences in how matter behaves. Even light, sound, and heat move through the dense water slightly differently, adding to the unique physical character of the deep ocean. Scientists have measured these differences with extreme precision. Atomic clocks, which track the vibrations of atoms to mark time, can detect tiny changes in the speed of time caused by gravity. Experiments placing these clocks at different heights, from mountain peaks to deep valleys, show that time ticks slightly faster where gravity is weaker and slower where gravity is stronger. Similar experiments conducted underwater confirm that depth adds a measurable, though tiny, delay. For instance, a clock placed at the bottom of the Mariana Trench would fall behind one at the surface by a fraction of a second over several years. While this discrepancy is not noticeable in daily life, it illustrates that the deep ocean is not only extreme in pressure and darkness, but also in the subtle ways that time itself behaves under the influence of gravity. The effect of gravity on time is known as gravitational time, dilation. It is more pronounced near massive objects, such as stars or black holes, where gravity is extreme. On Earth, the effect is far weaker, but it is still present. Deep waters provide a natural gradient of mass above a point, offering a slow, continuous change in gravitational pull from the surface down to the seafloor. The pressure of water represents the cumulative weight of the water column above, increasing the effective gravitational field very slightly. This makes the deep ocean an excellent natural setting to observe and measure the principle. Even though the differences are tiny, they are detectable by modern instruments. By comparing clocks at the surface, at mid-depths, and near the ocean floor, scientists can quantify the influence of water mass on the flow of time. High-pressure environments also affect the movement of particles and energy. Molecules in water experience forces from all directions, pressed together by the immense weight above. While these effects are not dramatic, they subtly slow motions at the microscopic level. This reduction in molecular speed contributes to slower chemical reactions and changes in the behavior of dissolved gases. The deep ocean's cold temperatures reinforce this effect, but the pressure itself is an independent factor. Water under high pressure is slightly denser, and the interactions between molecules become more ordered. Physical processes that occur in seconds near the surface may take longer in the abyss, giving rise to a world where the pace of change is governed by the immense, unyielding pressure above. Experiments with deep-diving submersibles often reveal practical implications of pressure and time differences. Mechanical systems must account for slower response times due to compressed fluids and altered material properties. Sensors that measure chemical reactions, sound, or currents operate slightly differently than at the surface, requiring calibration to account for pressure-related changes. Instruments such as accelerometers, gyroscopes, and timing devices can register subtle shifts in performance. Engineers and scientists consider these effects carefully to ensure accurate readings. Even small delays, when compounded over long durations or in extreme depths, become significant for research. Time in the deep ocean is a combination of physical reality and instrumental perception, both shaped by pressure and gravity. Gravity and pressure also influence sound in the deep ocean. Sound travels faster in denser water because the molecules are packed more closely together. At great depths, this results in measurable differences in the speed and direction of sound waves, creating zones where acoustic signals bend and concentrate. These variations are used by scientists to map the sea floor, track marine life, and study water movement. Since sound travels differently under pressure, the time taken for a wave to move from one point to another can differ slightly from expectations based on surface conditions. Acoustic measurements thus provide an indirect way to observe how the passage of time and energy is influenced by the extreme environment of the deep ocean. Water density, affected by pressure and temperature, also contributes to time-related effects on molecular and biological scales. Denser water changes diffusion rates, slowing how chemicals and nutrients move through the environment. Living organisms at depth experience slower metabolic rates because the delivery of molecules is slightly delayed and chemical reactions are inherently slower under pressure. Deep-sea microbes and invertebrates operate in an environment where energy is scarce and processes unfold with patience. Growth, reproduction, and movement are tuned to this slow pace. In this way, the physics of the ocean, gravity, pressure, and density interact directly with the passage of time for life forms, creating a rhythm distinct from the faster cycles near the surface. Time, dilation in the deep ocean, is a subtle, persistent phenomenon. It does not create noticeable differences for human observers in daily life, yet it is measurable with precise equipment. Clocks drift, molecules move more slowly, and physical processes extend over longer periods. This slow motion is reinforced by the deep ocean's cold and stable conditions. Together, these factors create a consistent environment where the passage of time is not just an abstract concept, but a measurable, physical reality shaped by the weight of water and the pull of gravity. Observing and recording these effects allows scientists to test fundamental physics while exploring one of the most extreme and mysterious parts of our planet. Even in the deepest trenches, time remains continuous. There is no pause, no sudden change, but the rate at which processes occur is gently stretched. Life, chemistry, and physical phenomena all operate under the quiet influence of pressure and gravity, moving in a slower, more deliberate rhythm. Each layer of water above adds weight. Each kilometer of depth contributes to the subtle shift in time's passage. While the effects are almost imperceptible without instruments, together they create an environment where the deep ocean exists in a unique temporal state, distinct from surface waters and ordinary human experience. It is a place where physics demonstrates the elegance of natural laws, showing that even on Earth, time is not uniform, but shaped by the mass of the world and the pressures it exerts. Studying these effects has practical applications. Precise knowledge of time differences is essential for navigation, deep-sea exploration, and understanding long-term chemical cycles. Atomic clocks allow researchers to account for gravitational and pressure effects, ensuring that data collected at depth is synchronized with measurements at the surface. These experiments highlight the connection between extreme environments and fundamental physics. By observing how time is influenced by water mass and pressure, scientists gain insight into principles that govern the universe, from the smallest molecules to the largest planetary bodies. The deep ocean thus becomes both a laboratory and a lens through which the subtle flow of time can be examined and understood. The deep ocean is cold, very cold, often just above freezing. Unlike surface waters, which warm and cool with the sun, the deep sea maintains a near constant temperature. In most regions below a few hundred meters, water hovers around 2 to 4 degrees Celsius. This persistent cold influences every aspect of the environment, from the movement of molecules to the behavior of living creatures. Molecular motion, the tiny vibrations and collisions that make up heat and energy, slows down in the cold. At higher temperatures, molecules move quickly, bumping into each other and exchanging energy with ease. In the deep ocean, this motion is reduced. Molecules travel more slowly, bonds form and break at a slower pace, and energy transfers gradually through the water. Every chemical reaction, every diffusion process, unfolds over an extended period, reflecting the ocean's slow, measured rhythm. The effect of low temperature on chemical reactions is significant. Reactions depend on molecules colliding with sufficient energy to rearrange into new compounds. In cold water, these collisions occur less often and with less force. Minerals dissolve at a slower rate, nutrients diffuse more gradually, and gases move through water at reduced speeds. Even simple processes, like the breakdown of organic matter, proceed with patience. A dead plankton cell sinking through the deep ocean can take months to fully decompose, much longer than the same particle in surface waters where warmth accelerates decay. Temperature controls the pace of change in every microscopic and macroscopic process, creating a deep ocean world where time is experienced through the slow unfolding of chemical and physical transformations. Temperature also governs entropy, the measure of disorder in a system. In warm environments, entropy increases rapidly as molecules move energetically and interactions multiply. In the cold, entropy increases more slowly. This affects the way reactions proceed and how energy spreads through the environment. In practical terms, this means that natural processes are tempered. Elements mix gradually. Reactions approach equilibrium at a leisurely pace, and the overall progression of events is drawn out. Deep-sea chemical cycles are, therefore, extended across years and decades. A molecule of carbon released at the surface may take a long journey before it reacts or settles in sediment, influenced by both the cold and the slow currents that carry it. Observing these cycles demonstrates that temperature is a master regulator of time in the ocean's depths. Hydrothermal vents provide a striking contrast within this cold world. In localized areas, water heated by magma escapes through cracks in the seafloor, sometimes reaching hundreds of degrees Celsius. Even here, the surrounding cold water acts as a buffer, absorbing heat slowly and regulating the spread of reactions. Minerals precipitate out of vent fluids over hours or days, forming structures like chimneys that grow slowly in the cold abyss. Chemical gradients drive life forms to exploit energy from dissolved compounds rather than sunlight. Microbes convert chemicals into energy at measured rates, their metabolisms adapted to the combination of high pressure and low ambient temperature. The contrast between hot vent water and the surrounding cold creates a zone where reaction rates vary sharply, but the overall pace is still slow compared to surface processes, highlighting the ocean's unique thermal regulation. Organic decay is another example of temperature's effect. Sinking particles of detritus from surface waters carry nutrients and carbon to the deep. In cold conditions, decomposition occurs gradually, allowing much of the material to reach the seafloor intact. This slow decay has ecological consequences. Deep-sea organisms rely on a steady but sparse supply of food. The preservation of organic matter in transit supports communities that would not survive rapid consumption or sudden abundance. Sediments accumulate organic content over centuries, layer by layer, as cold temperatures reduce microbial activity and chemical breakdown. In this way, the temperature of the deep ocean not only influences chemistry, but also shapes ecosystems and the flow of energy through the marine food web. The interplay of temperature and pressure also affects solubility. Cold water can hold certain gases more effectively, including oxygen and carbon dioxide. Dissolved oxygen supports life while carbon compounds enter long-term cycles. Reaction rates involving these gases are slower than in warmer water. For example, carbonate reactions that form sedimentary structures or neutralize acids progress at a gentle pace, sometimes taking decades to produce measurable changes. These slow processes illustrate how physical conditions regulate the timing of chemical transformations in the ocean, reinforcing the idea that temperature is a primary determinant of the rhythm of deep-sea processes. Molecular motion at depth affects diffusion, the spreading of particles from areas of high concentration to low. In cold water, diffusion slows, meaning that nutrients, dissolved gases, and ions move less quickly through the environment. This has cascading effects on both chemical and biological systems. Microbes and invertebrates must adapt to the slow arrival of resources, often developing low-energy metabolisms suited to gradual supply. Even when currents transport material, the underlying molecular movement is sluggish, moderating the pace of life and chemical cycling. The deep ocean thus operates on extended timescales, where physical laws set a deliberate tempo for every interaction. Temperature also interacts with time in ways that influence geological processes. Cold conditions reduce rates of mineral dissolution and sediment alteration. Minerals delivered from rivers or hydrothermal vents accumulate slowly, forming structures that record history over centuries. Trace elements in sediments provide a record of past ocean chemistry, their positions preserved because reactions that would redistribute them occur so slowly. By examining cores from the sea floor, scientists can read a timeline of environmental change, where the cold of the deep ocean ensures that chemical processes do not erase the past. Time in these sediments is marked not by days or years alone, but by the slow, cumulative unfolding of reactions under constant low temperature. Biological rhythms also reflect the influence of cold. Deep-sea animals grow slowly, reproduce over long periods, and maintain low metabolic rates. Microbial communities, fundamental to nutrient cycling, operate with patience, converting organic matter into energy at a steady pace. Enzyme activity is reduced by low temperature, meaning chemical pathways function with careful moderation. These biological processes echo the physical and chemical slowness imposed by the environment. In effect, the cold of the deep ocean stretches the passage of time for living organisms, aligning life cycles with a deliberate tempo of chemistry and molecular motion. Observations confirm that temperature governs pace. Scientists tracking decomposition, chemical gradients, and biological activity see clear correlations. Organic particles descend through the water column slowly, microbe activity is extended, and reactions take longer than at the surface. Experiments with tracers show delayed diffusion and gradual changes in chemical composition. Even in regions influenced by hydrothermal vents or deep currents, the cold maintains a baseline pace, moderating the rate of change across the broader environment. Every measurement, every observation reinforces the principle that temperature is central to the way time is experienced in the deep ocean. Ultimately, the deep ocean's low temperature creates a natural calendar for processes of all kinds. Molecular motion is slowed, reactions unfold gradually, and energy transfer is deliberate. Live sediments and chemical cycles all operate within this extended time frame. Observational evidence from multiple sources, sediment cores, in situ experiments, and long-term monitoring demonstrates that cold water stretches time without stopping it. The result is a consistent, predictable world where changes occur slowly and steadily, allowing scientists to study processes that would be too rapid to observe near the surface. Time, shaped by temperature, flows in a patient rhythm, giving the deep ocean its unique temporal character. The ocean is never still. Even in the deepest regions, water moves in slow but persistent flows. These movements are not like the waves we see at the surface, breaking and retreating in moments. Instead, deep currents glide along invisible highways, guided by differences in temperature and salinity. This circulation, often called thermohaline circulation, links the entire global ocean, connecting polar regions with the tropics and shallow waters with abyssal depths. Warm, less dense water moves across the surface, while cold, dense water sinks and travels along the ocean floor. These flows operate on scales of years to centuries, far slower than the currents near coastlines or in surface layers. Observing them is a lesson in patience, as each parcel of water traces a journey that may last hundreds of years before returning to its point of origin. Thermohaline circulation depends on the careful balance of heat and salt. When water at the poles cools and becomes denser, it sinks, displacing water below and setting a conveyor belt in motion. In this way, the deep ocean stores cold water, distributing it around the globe. Similarly, salinity differences, caused by evaporation or melting ice, alter density and influence the direction of flow. The resulting currents are steady but slow. A droplet of water at high latitude might travel to the equator in a few decades, then return to polar waters over a century or more. This slow pace contrasts sharply with the surface currents influenced by winds, tides, or storms, which can move water hundreds of kilometers in a matter of weeks or months. The deep ocean operates on a scale of time that is nearly imperceptible in human terms, yet it shapes the climate and chemical balance of the planet. These currents act as repositories for heat and chemical elements. As water moves along the thermohaline conveyor, it carries energy from warm regions to colder regions, helping to regulate global temperatures. Deep waters absorb and hold this energy for long periods, releasing it only slowly. Similarly, nutrients, carbon, and other chemical compounds are transported along the flow. Elements released at one location can travel vast distances, taking decades or centuries to reach another part of the ocean. The slow pace allows these materials to accumulate and interact gradually, creating a stable and persistent system. In this way, the deep ocean functions as both a storage space and a delivery system, maintaining balance over long timescales and contributing to the continuity of Earth's climate and chemistry. Shallow waters behave very differently. Currents near the surface respond rapidly to wind, tides, and temperature changes. Water can move quickly from one place to another, often returning within days or weeks. Waves, eddies, and seasonal flows create a dynamic environment where chemical concentrations and temperatures fluctuate rapidly. In contrast, the deep ocean's slow, dense flows change little over short periods. Nutrient concentrations remain relatively stable, and temperature variations are minimal. Organisms adapted to these conditions experience an environment where time feels stretched, where events unfold over decades rather than hours or days. For scientists, these differences are critical. Observing shallow waters cannot reveal the gradual accumulation, movement, and transformation of materials that occur in the abyss. Only by tracking deep currents over long periods can the slow rhythm of the ocean be understood. The slow pace of deep currents also affects climate modeling. Scientists rely on data from these flows to predict long-term trends. The redistribution of heat and chemicals influences weather patterns, ocean productivity, and the global carbon cycle. Small changes at the surface may propagate slowly through the deep ocean, only becoming noticeable after many years. Understanding the timescales of thermohaline circulation is therefore essential for accurate forecasting. These currents act as the planet's memory, holding information about past conditions and slowly integrating it into the broader system. Studying them allows scientists to see the ocean's history in motion, tracking processes that extend far beyond human lifetimes. Currents also interact with the seafloor and underwater topography. As water moves, it follows paths shaped by ridges, valleys, and trenches. These features influence the speed and direction of flow, creating regions where currents slow, accelerate, or spiral. Over centuries, these patterns transport sediments, nutrients, and even heat in consistent ways. Water traveling along the ocean floor may encounter obstacles that divert it, stretching the journey further. Yet, despite these complexities, the system remains orderly, with dense water moving predictably along established routes. This stability contrasts with the chaotic mixing at the surface, reinforcing the sense of extended time in the deep ocean. The storage of chemical elements in deep currents has consequences for life and biogeochemical cycles. Carbon, for example, can remain trapped in deep water for centuries before resurfacing. Nutrients released from decaying organic matter are slowly transported to distant regions, supporting deep-sea communities far from their origin. Oxygen levels in deep waters are maintained over long distances, sustaining life in isolated pockets. By acting as a reservoir, these currents link distant parts of the ocean and regulate the timing of biological and chemical processes. The slow movement ensures that the deep ocean functions as a stable, patient environment, where time is experienced on the scale of generations and centuries, rather than days or seasons. Even heat itself is preserved in these flows. Warm water sinking from tropical regions mixes slowly with cold polar water, carrying thermal energy across oceans. The process is gradual, and the energy is released in small increments as water slowly rises elsewhere. This slow redistribution is essential for maintaining a relatively stable global climate. In comparison, surface layers respond immediately to sunlight, absorbing heat during the day and releasing it at night. The deep ocean's delayed response illustrates a temporal separation. Surface waters react quickly, while the abyss maintains a slow, steady course. Life and chemical reactions in the deep are tuned to this extended rhythm, operating within a frame of time set by the patient movement of currents. Observation of deep currents is challenging. Measuring devices must survive high pressure and low temperatures for long periods. Instruments track temperature, salinity, and velocity over decades to capture the full picture. Drift buoys, deep floats, and moored sensors reveal the movement of water masses with remarkable precision. The data confirm that the deep ocean's flows are slow but persistent, spanning hundreds to thousands of kilometers over centuries. This continuity highlights the contrast between the rapid changes of shallow water and the enduring pace of the abyss. Each measurement contributes to understanding how the ocean's long-term memory stores information about energy, chemistry, and environmental change. The interaction between currents and time is also evident in sediment transport. As water moves along the sea floor, it carries fine particles, distributing them over long distances. This transport occurs gradually, layer by layer, recording the passage of centuries. Sediment cores reveal patterns that mirror current flows, showing how slow movement shapes the accumulation of materials and the timing of geological processes. The deep ocean's currents are thus both conveyors and timekeepers, demonstrating the connection between physical movement and extended temporal scales. Through these flows, scientists see time as a continuous, measured process, guided by the patient circulation of water across the globe. Even the perception of time in deep systems is shaped by currents. Organisms living in these environments adapt to slow, stable flows. Growth, feeding, and reproduction are synchronized with the steady movement of water and nutrients. Life is paced according to the current's rhythm, not the surface world's rapid cycles. For microbes, invertebrates, and larger deep-sea species, survival depends on the predictability of these flows. In this sense, time in the deep ocean is experienced not only physically, but biologically. Currents dictate the rhythm of life, chemical reactions, and the redistribution of energy, creating a consistent, enduring environment that reflects the slow, patient nature of the abyss. Studying these currents allows scientists to understand how the deep ocean connects past and future. Water that sank decades ago carries information about historical climate, chemical composition, and temperature. By the time it returns near the surface, it integrates centuries of environmental history. This perspective demonstrates that the deep ocean is not just a physical space, but a temporal archive where processes are extended and measured in long intervals. Currents act as both transporters and preservers of time, moving heat, chemicals, and nutrients with deliberate slowness. Observing their behavior reveals the layered, patient rhythm of the ocean, a rhythm that governs the deep environment and gives a tangible sense of time unfolding across centuries. Life in the deep ocean exists under extreme conditions. Darkness dominates, pressure is immense, and temperatures are near freezing. Yet, this world is not empty. Organisms have adapted to survive, and their rhythms reflect the slow passage of time in the abyss. Many species produce their own light through bioluminescence. Tiny bacteria, small fish, and even some invertebrates generate faint glows, often used for communication, hunting, or camouflage. The light is subtle and controlled, produced only when needed, in contrast to the bright, constant sunlight of surface waters. Bioluminescence is a signal tuned to the patient pace of the deep ocean, an adaptation to an environment where energy is scarce and rapid action is rarely possible. Metabolism in deep-sea creatures is also slow. Life operates on minimal energy budgets. Fish, worms, and crustaceans consume food gradually, digesting over hours or days rather than minutes. Microbes break down organic matter at rates far slower than at the surface, consistent with low temperatures and high pressure. Growth occurs incrementally, with tiny gains over months and years. Some species live for decades or even centuries. Deep-sea corals, for example, grow only a few millimeters each year, but can survive for hundreds of years. Giant tube worms near hydrothermal vents may live for several decades, maintaining slow but steady development. The combination of cold, pressure, and limited food supply dictates a life pace that is deliberate and sustained. Biological clocks in the deep ocean have adapted to the absence of sunlight. Circadian rhythms, which on land or at the surface often follow a 24-hour cycle, operate differently when light cues are absent. Many deep-sea species rely on internal timers that align with feeding cycles, reproduction schedules, or the gradual movement of currents. Some microbes respond to nutrient availability transported by slow flows, while larger animals follow seasonal patterns tied to the sinking of organic matter from surface waters. Even in constant darkness, organisms maintain a sense of time, though it is extended and shaped by the environment rather than by the cycle of day and night. Certain species provide clear examples of slow biological rhythms. Giant tube worms attached to hydrothermal vents derive energy from symbiotic bacteria that process chemicals in vent fluids. The worms grow gradually, and their development reflects the steady supply of energy rather than rapid external cues. Deep-sea corals form intricate structures over centuries, adding small amounts of calcium carbonate each year. Abyssal fish often grow slowly and reproduce late in life, strategies that match the slow accumulation of resources in their environment. Each species demonstrates that life in the deep ocean is synchronized with the measured pace of chemical, thermal, and physical processes, rather than surface rhythms that rely on sunlight and daily temperature changes. The link between environmental time cues and biological perception is subtle but real. Nutrient pulses, gentle shifts in temperature, and slow current movements act as signals for feeding and reproduction. Organisms respond over extended periods, matching their internal processes to the gradual pace of the environment. In effect, the deep ocean sets its own clock. Life there is tuned to centuries-long rhythms of chemical cycling, sediment deposition, and water movement. Even predators and prey follow these extended patterns, hunting, feeding, and reproducing according to signals that operate over weeks, months, or years rather than hours. Adaptations extend to sensory and behavioral mechanisms. Many animals use bioluminescence to attract mates or prey, timing flashes precisely in response to faint signals in their environment. Predators detect subtle vibrations in water, responding slowly and efficiently to conserve energy. Prey species move minimally, using low metabolic output to survive between rare food events. These strategies demonstrate that the passage of time for deep-sea organisms is not perceived as rapid or urgent. Rather, it unfolds in a steady, consistent rhythm, shaped by environmental constraints. The slow pace of growth, feeding, and reproduction is a reflection of the temporal scale imposed by the deep ocean itself. Even microorganisms follow extended temporal patterns. Bacteria and archaea metabolize nutrients at rates dictated by cold and pressure. Enzyme activity occurs gradually. Cell division is slow, and population changes happen over long intervals. These microbes form the foundation of deep-sea ecosystems, supplying energy to higher organisms in a measured fashion. The interplay between slow metabolism and steady resource availability maintains stability in communities, allowing ecosystems to persist over centuries. Time in these microbial systems mirrors the physical environment, moving at a pace set by temperature, pressure, and nutrient transport. Energy efficiency is a key driver of biological rhythms. In an environment where resources are scarce, organisms cannot afford rapid consumption or wasteful activity. Slow feeding and measured digestion maximize energy use. Growth and repair processes proceed incrementally, ensuring survival in an environment that changes gradually. Life in the deep ocean is therefore a model of patience, where biological clocks are aligned with environmental rhythms and chemical processes, all unfolding over extended periods. The pace of life mirrors the pace of the water, the temperature, and the currents. The reproductive cycles of deep-sea species are similarly slow. Many fish produce few offspring, which develop over long periods. Corals and sponges release gametes in rare synchronized events, triggered by slow environmental changes rather than daily cues. Giant tube worms reproduce through gradual growth and steady maturation, their life histories spanning decades. These patterns are consistent with the slow accumulation of nutrients, the gradual flow of water, and the steady pace of chemical reactions. The biological clocks of these organisms operate not on a daily schedule, but on a rhythm set by the patient movement of the ocean itself. Observational evidence confirms the connection between environmental time cues and organism behavior. Long-term studies using submersibles, stationary cameras, and sensors show that deep-sea species adjust activity to gradual changes in food availability, chemical gradients, and temperature. Feeding patterns are often sporadic but predictable over weeks or months. Growth rates align with chemical and thermal conditions. Reproduction is timed to subtle seasonal or environmental shifts. In all cases, the rhythm of life reflects the measured pace of the deep ocean. Organisms have evolved to integrate these slow cues into their biological clocks, experiencing time differently from surface-dwelling species. Even mobility is influenced by the pace of the environment. Abyssal fish swim slowly, conserving energy. Crustaceans crawl along the sea floor, responding gradually to chemical or tactile signals. Movement is efficient, tuned to the sparse availability of food and the steady, gentle currents that carry nutrients. Every action reflects an adaptation to extended temporal scales, where rapid or sudden motion is unnecessary and often wasteful. Life in the deep ocean exemplifies how environmental conditions shape not only the speed of physical processes, but also the perception of time. For living organisms, energy transfer through the food web mirrors this slow rhythm. Organic particles sinking from the surface support microbes, which in turn sustain small invertebrates, which feed larger animals. Each step unfolds gradually, with energy passed along in small, steady increments. No event is rushed, no cycle abrupt. Deep-sea ecosystems operate as extended chains, each link paced by temperature, pressure, and resource availability. Observing these patterns shows how environmental time cues dictate the timing of biological processes, creating a world where life moves deliberately, in step with the slow pulse of the ocean. Ultimately, biological rhythms in the deep ocean are a reflection of its physical and chemical environment. Organisms grow, feed, reproduce, and interact according to extended temporal scales. Bioluminescence, metabolism, growth, and reproduction all follow measured, predictable rhythms that differ greatly from surface species. Time in the deep ocean is therefore both a physical phenomenon, governed by pressure and temperature, and a biological reality, experienced through the rhythms of life itself. The deep-sea world is a testament to the patient, deliberate unfolding of time, where every process is tuned to the enduring pace of the environment. Sediments in the deep ocean accumulate slowly, layer by layer, over decades, centuries, and even millennia. Particles of dust, minerals, and the remains of tiny organisms descend from the surface, settling gently onto the sea floor. The cold, high-pressure environment of the abyss prevents rapid decomposition or disruption, allowing these particles to remain largely undisturbed. In shallow waters, sediments can be shifted by waves, storms, or tides, but in the deep ocean, the steady deposition creates a gradual, ordered record. Each layer is like a page in a book, documenting the slow passage of time and capturing the conditions of the water above. Over thousands of years, these layers build thicknesses of mud, clay, and ooze, forming a natural archive of Earth's history. Microfossils preserved in these sediments are particularly valuable. Tiny shells from plankton and other microorganisms settle alongside inorganic particles. Their chemical composition, including ratios of isotopes, reflects the temperature, salinity, and nutrient conditions of the water in which they lived. Because the sediments accumulate so slowly, microfossils remain intact, providing a clear record of past environments. Scientists can extract cores from the sea floor and examine these fossils to reconstruct changes in ocean chemistry, temperature, and productivity over thousands of years. Each core is a vertical timeline, capturing the history of ocean conditions in remarkable detail, preserved by the cold and pressure of the deep. Chemical signatures in sediments add another layer of information. Elements like carbon, nitrogen, and trace metals enter the ocean from rivers, volcanic activity, and atmospheric deposition. As these elements settle in the deep, they record the composition of water at the time of deposition. Radioactive isotopes, such as carbon-14, allow scientists to date layers with precision. Other isotopes reveal changes in ocean circulation or the introduction of oxygen-depleted zones. These chemical records complement fossil evidence, providing a multidimensional view of the ocean's history. Together, they form a chronological framework that ties the slow passage of time in the deep ocean to larger geological processes. Deep-sea sediments act as natural time capsules. Once deposited, a layer can remain undisturbed for centuries or millennia, preserving evidence of environmental conditions far beyond the scale of human observation. Events such as volcanic eruptions, shifts in ocean currents, or sudden increases in biological productivity leave detectable traces. Layers may show changes in particle size, chemical composition, or fossil content. By studying these features, scientists can identify cycles, anomalies, and transitions, building a picture of Earth's past climate, ocean chemistry, and even mass extinction events. Each layer provides insight into processes that occurred long before humans observed the planet, linking the passage of time in the deep ocean to the much larger scale of geological time. Ocean cores are the primary tool for accessing these records. Scientists use drilling vessels and specialized coring equipment to extract long cylinders of sediment. The cores preserve the sequence of layers exactly as they settled, maintaining the chronological order of deposition. Analyzing the layers reveals variations in composition, particle size, and fossil content. Subtle changes indicate shifts in surface productivity, ocean temperature, and circulation patterns. For example, an increase in diatom remains may signal a period of high nutrient availability, while changes in isotopic ratios can point to glacial or interglacial cycles. Ocean cores allow scientists to trace Earth's climatic history over tens of thousands of years, demonstrating the slow but persistent passage of time recorded in deep sediments. Sediment accumulation rates in the abyss are exceptionally slow. In many regions, the ocean floor gains only a few millimeters of sediment per year. In some areas, such as the Central Pacific, the rate is less than a millimeter annually. This slow deposition preserves detailed records that would be erased by faster accumulation or disturbance. Even over millennia, these small annual increments build extensive archives of environmental history. Scientists can identify layers representing specific events, such as volcanic ashfalls or sudden shifts in nutrient supply. Each layer, though thin, carries critical information about the ocean's past, illustrating how slow processes in the deep ocean extend the perception of time far beyond the human scale. Sediments also record changes in ocean circulation. Thermohaline flows transport particles from distant regions, depositing them in predictable patterns. Variations in sediment composition reveal changes in current strength or direction over centuries. For example, layers rich in specific minerals may indicate stronger flow from a particular region, while shifts in isotopic composition can reflect changes in water mass origins. These deposits capture the slow movement of the ocean's interior, preserving a timeline of physical processes alongside chemical and biological records. By examining these patterns, scientists can reconstruct the history of deep ocean circulation, connecting the pace of currents to the broader geological story. Organic material in sediments further reflects the slow rhythm of the deep ocean. Particles of plankton, detritus, and other organisms sink gradually, decomposing slowly under cold, high-pressure conditions. The degree of preservation provides information on oxygen levels, microbial activity, and chemical reactions at the time of deposition. Carbon stored in sediments forms part of the global carbon cycle, with some fraction locked away for thousands of years. This long-term storage links deep ocean processes with planetary systems, showing that the passage of time in sediments is not merely local, but interconnected with Earth's climate and biogeochemistry. Sediment records also allow scientists to observe cycles of glacial and interglacial periods. Isotopic analysis of microfossils can indicate ocean temperature variations corresponding to ice ages. Layers with higher dust content may reflect periods of aridity or increased wind activity. Shifts in trace elements reveal changes in ocean productivity or nutrient supply. By comparing cores from different locations, researchers can reconstruct a global picture of climate change over tens of thousands of years. The deep ocean acts as a slow, persistent recorder, extending the temporal perspective far beyond human experience and providing evidence that the Earth has been shaped by gradual cumulative processes. The connection between deep ocean time and geological timescales is profound. Sediments deposited over millennia link short-term processes, such as sinking particles and chemical reactions, to long-term changes in Earth's climate, tectonics, and sea level. Every layer is a record of time passing at different scales, from days and months marked by seasonal deposition to centuries reflected in accumulation rates and millennia captured in isotopic composition. By studying these layers, scientists gain insight into the continuity and duration of processes that govern the planet. The deep ocean is thus both a laboratory for observing slow physical and chemical dynamics and a repository of geological memory. Even the oldest sediments preserve subtle details about environmental change. Minor variations in composition reveal shifts in temperature, salinity, and nutrient availability. Changes in particle size or fossil content record episodes of increased erosion, volcanic activity, or oceanic current shifts. The deep ocean archives events that occur over thousands of years in a single sequence, maintaining a continuous timeline. By extracting and analyzing these sediments, scientists can trace the history of the ocean and the Earth itself, understanding the passage of time not only as a human measurement, but as a fundamental feature of the planet's natural processes. Ultimately, deep ocean sediments serve as tangible evidence that time in the abyss is extended, continuous, and measurable. The accumulation of layers, preservation of microfossils, and chemical records provide insight into processes that unfold over centuries and millennia. Ocean cores reveal Earth's climatic past, documenting cycles of temperature, circulation, and productivity. Through these sediments, the slow rhythms of the deep ocean connect with geological time, offering a perspective that spans far beyond human experience. Time in the abyss is recorded in mud, ooze, and microfossils, a patient archive of planetary history that allows scientists to read the story of Earth over vast scales. Sound moves differently in the deep ocean than at the surface. The SOFAR channel, a layer where sound waves travel efficiently over long distances, allows noises to move for hundreds or even thousands of kilometers. This channel occurs because water density changes with depth temperature, and pressure, bending sound waves toward the center of the layer. Low-frequency sounds, such as whale calls or artificial pings from research instruments, can propagate with little loss of energy. For animals and researchers, this means that signals sent across the ocean take longer to arrive than in shallow waters, where sound is quickly absorbed or scattered. The deep ocean's physical properties extend the travel time of acoustic signals, creating a slower sense of auditory events over distance and time. Light, in contrast, hardly penetrates to these depths. Sunlight fades within the first few hundred meters, leaving most of the ocean in darkness. Only dim blue light reaches below, and even that is absorbed quickly by water molecules. Beyond a few thousand meters, no natural light remains, and organisms must rely on bioluminescence or artificial illumination. Navigation becomes challenging in this darkness. Visual cues are limited, and distances appear compressed because faint glows fade rapidly. Animals and submersibles experience time differently in this environment. Movements that might seem quick near the surface feel slower, in part because visual perception is limited and energy must be conserved. Light scarcity shapes the pacing of life, prompting slow, deliberate motion and careful timing of activity. Navigation and communication depend on these physical constraints. Marine animals, such as whales and deep-sea fish, use sound to locate prey, mates, and obstacles. The delay in sound travel over long distances forces them to interpret signals cautiously. Predators must wait for echoes to return before acting, while prey may respond only after detecting faint vibrations. Deep-diving submersibles operate similarly, sending sonar pulses that take measurable time to travel and return from the seafloor or distant objects. Engineers account for these delays when navigating or mapping terrain. The combination of slow light and long-distance sound transmission effectively stretches the temporal experience for both life forms and instruments. Experiments with sonar have revealed just how patient the deep ocean requires researchers to be. Sonar pings propagate along the SOFAR channel, returning echoes that take seconds to minutes depending on distance. Interpreting these echoes requires careful calculation and adjustment for water density, temperature, and pressure. Even small changes in depth or salinity alter the travel time of sound. Scientists have learned to calibrate instruments with precision, recognizing that delays are not errors, but intrinsic properties of the environment. In this way, measurements themselves reflect the slow passage of time in the abyss, where physical signals do not move instantly, but unfold across measurable intervals. Deep-diving submersibles further illustrate this extended perception of time. As they descend, instruments record pressure, temperature, chemical composition, and sonar reflections. Each measurement is influenced by the physical medium. The speed of sound, absorption of light, and water movement all affect readings. Operators must wait for data transmission, observe subtle shifts, and interpret patterns slowly. Even small tasks, such as detecting features on the seafloor or tracking organisms, require patience. The environment imposes a natural temporal extension, where immediate action is replaced by methodical observation and careful measurement. Time for researchers, like time for life in the deep, is not rapid but deliberate. Animals have adapted to these slow physical cues. Fish and invertebrates use bioluminescent flashes for communication, timing them according to slow changes in their surroundings. Predators and prey respond to vibrations over distances that stretch over seconds or minutes. Movements are measured to conserve energy, and hunting strategies are paced with the slow feedback of sound and light signals. Even reproduction and migration depend on understanding delayed environmental cues. The deep ocean teaches life to interpret a world where sensory information arrives gradually, creating a sense that events unfold more slowly than they would in shallow sunlit waters. Sound and light influence not only perception, but also measurement of time itself. Acoustic signals take time to propagate. Light is absorbed and scattered, delaying visual confirmation. Biological processes are synchronized to these slow cues. Animals sense, react, and move according to the timing imposed by their environment. Human instruments must account for these delays to capture accurate data. Observing and interpreting events in the deep requires acknowledging that the physical world here operates on extended timescales. Delays in sensory perception, whether by sonar or bioluminescent signals, create a natural expansion of time, slowing responses, reactions, and interactions. The SOFAR channel also connects distant regions of the ocean. A signal emitted in one hemisphere may be detected thousands of kilometers away. The extended travel time allows researchers to study environmental changes over space and time, revealing the slow integration of energy and information across the deep. Patterns of temperature, salinity, and pressure influence propagation, demonstrating how physical conditions govern the rate at which the environment communicates with itself. The deep ocean becomes a place where time is not only a human measurement, but a property that affects every signal, pulse, and motion. Light's extreme attenuation reinforces the sense of slow time. Deep-sea creatures emit flashes only when necessary, avoiding waste of energy. Movements are deliberate, and hunting or mating behaviors proceed over long periods. Even when artificial lighting is used, shadows and reflections move slowly across the sea floor due to sparse illumination. Human observation of these behaviors must account for the fact that visual cues are delayed, often subtle, and require careful interpretation. Life has adapted to match the slow tempo imposed by light scarcity and sound propagation, integrating physical limits into survival strategies. Experiments with submersibles and remote-operated vehicles show that task completion takes longer than at the surface. Surveying a small area may require hours because sonar reflections need time to travel. Data must be processed slowly, and movements are cautious to avoid damaging instruments. Similarly, mapping geological features or tracking slow-moving animals demonstrates that time is extended in practice, not just in theory. The environment dictates a pace for observation, reinforcing the impression that events in the deep unfold more slowly than those above. Even energy transfer through sound is affected. Vibrations move gradually through dense water, and subtle differences in water temperature and salinity bend or scatter the waves. This impacts how animals detect prey or communicate. Signals may arrive seconds or minutes later than expected, requiring adjustment of behavior. Sensory feedback is inherently delayed, producing a temporal stretching that affects decision-making. Life in the deep ocean therefore experiences time not as a rapid succession of events, but as a slow, continuous unfolding guided by physical laws. Chemical and biological interactions also follow these slow cues. Nutrients transported by currents arrive over extended periods. Predators follow these flows cautiously, timing their feeding and reproduction with gradual changes in resource availability. Microbes respond to subtle chemical gradients, moving and metabolizing in a manner attuned to the slow diffusion of molecules. The combined effect of slow sound, light scarcity, and environmental pacing shapes every aspect of life, creating a world where the rhythm of events is long and measured. The deep ocean operates in a deliberate, extended time frame, where every perception, measurement, and interaction is tempered by the environment. Ultimately, sound, light, and the perception of time are intertwined in the deep ocean. Acoustic signals travel along the SOFAR channel. Light is absorbed almost completely, and sensory systems, both human and biological, adjust to the slow arrival of information. Delays are natural, inevitable, and essential to understanding the deep. Life has adapted to these conditions, moving and responding in tune with extended environmental cues. Observations, experiments, and long-term studies confirm that the physical properties of water create a sense of slower time, where every event unfolds at a pace dictated by the laws of physics and the patient rhythm of the abyss. Time is not halted, but stretched, experienced more deliberately by organisms and instruments alike, in harmony with the environment that surrounds them. Human exploration of the deep ocean requires specialized tools and equipment designed to withstand extreme conditions. Manned submersibles, with reinforced hulls and life support systems, allow researchers to descend thousands of meters below the surface. These vessels face pressures hundreds of times greater than at sea level, temperatures near freezing, and complete darkness. Every mechanical component must function precisely under these conditions, as even a small failure can have serious consequences. The design of submersibles is dictated not only by safety, but also by the need to record data accurately, as delays and distortions can compromise measurements in this patient, slow-paced environment. Deep-sea probes complement manned missions. Autonomous instruments, equipped with cameras, sensors, and sampling devices, can remain at depth for extended periods. These unmanned vehicles collect information continuously, monitoring temperature, salinity, chemical composition, and biological activity. The extreme pressure slows mechanical responses, and careful calibration is required to ensure that instruments register events in real time. Even small movements or adjustments take longer than they would at the surface, illustrating how the environment extends operational time. Engineers and scientists must account for these delays, planning missions with a temporal awareness that matches the rhythm of the deep ocean. Long-term deployments are particularly valuable. Sensors anchored to the sea floor or suspended at depth record data over weeks, months, or years. Continuous monitoring allows researchers to observe slow changes in currents, temperature, and chemical concentrations. Events that may seem instantaneous at the surface unfold gradually at depth. For example, the arrival of nutrient-rich water transported by thermohaline currents may be detectable over days or weeks. Long-term observation captures these subtle shifts, providing insight into temporal processes that cannot be measured during short dives or surface observations. Persistence in monitoring is essential to understanding the slow dynamics of the abyss. Atomic clocks are among the most precise tools used in deep ocean research. These clocks measure time to billionths of a second, and when deployed at depth, they reveal minute differences in the passage of time caused by gravity and pressure. Experiments have shown that clocks at the bottom of the ocean run slightly faster than identical clocks at the surface due to gravitational time dilation and the distribution of Earth's mass. These differences are imperceptible in daily life, but measurable with modern instruments. Deep-sea research combines these clocks with environmental sensors, integrating physical, chemical, and temporal measurements into a comprehensive view of the ocean. The abyss thus becomes a laboratory, not only for studying water, chemistry, and life, but also for observing the flow of time itself. Mechanical instruments at depth also respond more slowly than at the surface. Hydraulic arms, sampling devices, and camera mechanisms operate under extreme pressure, where even small movements face resistance from dense water. Delays in actuation are inevitable, requiring careful anticipation by operators. Tasks that might take seconds at the surface can require minutes in the abyss. The environment stretches time for human activity, demonstrating that the slow pace of the deep ocean influences not only natural processes, but also the rhythm of exploration. Scientists must move deliberately, coordinating actions with the patient tempo of their instruments and surroundings. Observation of micro-time differences is one of the remarkable achievements of deep-sea instrumentation. Variations in clock rates, delays in mechanical responses, and slow propagation of signals reveal that time is not uniform across the planet. Experiments have documented differences of billions of seconds between the surface and the ocean floor. While these discrepancies are tiny, they provide insight into fundamental physics and the influence of mass, pressure, and depth on temporal measurement. Researchers have learned to interpret these differences as part of the natural rhythm of the deep ocean, integrating them into models of physical, chemical, and biological processes. Sensors record slow variations in temperature, salinity, and chemical composition over long periods. These measurements reveal processes that unfold gradually, from the settling of particles in sediments to the movement of deep currents and diffusion of dissolved gases. Instruments must operate continuously, surviving months or years without maintenance. The design of these systems reflects the need for patience. Automated sampling, redundancy, and careful calibration ensure that time-sensitive data is accurate despite the slow response of mechanical and electronic components. In this way, human exploration aligns with the extended timescale of the environment itself. Submersible observation also allows scientists to see the effects of time on biological processes. Long-lived organisms, such as deep-sea corals or giant tube worms, are monitored over months and years. Growth, feeding, and reproductive cycles are recorded, showing how life adapts to extended temporal rhythms. Cameras and sensors capture incremental changes in behavior and environment, emphasizing the slow pace of events. Human observation, constrained by technology and environmental conditions, mirrors the natural pace of the abyss, highlighting the relationship between time, measurement, and biological processes. Communication between submersibles and surface vessels relies on acoustic signals, which, as previously noted, travel slowly over distance. Transmission delays must be accounted for in operations, reinforcing the sense that the environment extends the time required for measurement and control. Real-time monitoring is never truly instantaneous, and careful synchronization of instruments is necessary. The deep ocean imposes a deliberate tempo, affecting not only natural events, but also human attempts to observe and interact with them. Delays are a fundamental part of exploration, just as they are part of life and physical processes in the abyss. Data collected from deep ocean instrumentation contributes to understanding the subtle passage of time in this extreme environment. From atomic clocks to temperature and chemical sensors, every measurement integrates the effects of pressure, gravity, and slow physical processes. Instruments capture small but significant temporal differences, linking observations of life, chemistry, and physics to broader concepts of time dilation and environmental pacing. By combining long-term monitoring with high-precision tools, scientists are able to see the deep ocean as both a space of physical extremes and a realm where time unfolds differently than at the surface. Repeated observations highlight the need for patience and precision. Deploying and retrieving instruments requires careful planning, accounting for currents, pressure, and the delayed responses of devices. Data analysis takes additional time, as scientists interpret slow changes in chemistry, temperature, and physical movement. Every aspect of human exploration, from descent to measurement, is extended in temporal scale, mirroring the natural rhythms of the deep ocean. Exploration becomes an exercise in aligning human activity with the measured, deliberate passage of time in an environment that operates on centuries-long processes. Ultimately, human instrumentation reveals that the deep ocean is not only physically extreme, but temporally distinctive. The combination of high pressure, slow currents, low temperatures, and extended sensory delays creates an environment where time is stretched and measured in fine increments. Manned submersibles, autonomous probes, and atomic clocks allow scientists to observe minute differences in the passage of time, demonstrating that the abyss is a laboratory for both natural and physical processes. Through careful observation and patient measurement, researchers gain insight into how time is experienced differently at depth, integrating biological, chemical, and physical rhythms into a coherent understanding of the ocean's slow, deliberate pace. The deep ocean thus provides a unique context for studying time itself. Instruments record delays, mechanical responses, and microtime differences, showing that the rhythm of the abyss is slower and more measured than at the surface. Human exploration, constrained by technology and physics, aligns with the pace of the environment. Every observation, experiment, and deployment confirms that the passage of time in the deep is real, measurable, and influenced by extreme conditions. The patient unfolding of events, whether physical, chemical, or biological, is revealed through careful instrumentation, demonstrating that time at depth is both a physical phenomenon and an essential factor shaping life and observation in the abyss. The slow pace of processes in the deep ocean has profound effects on Earth's climate, ecology, and physics. Carbon storage is one of the most important of these effects. Particles rich in carbon sink from surface waters, gradually depositing on the seafloor. In the cold, high-pressure environment, decomposition is extremely slow. Organic carbon can remain trapped for centuries, preventing immediate release into the atmosphere. This long-term storage acts as a natural buffer against rapid climate change, regulating the concentration of carbon dioxide in the air over extended periods. The slow accumulation ensures that the deep ocean is a patient partner in the global carbon cycle, gradually absorbing what surface systems cannot handle quickly. Nutrient cycles are equally affected by slow deep ocean processes. Elements such as nitrogen, phosphorus, and trace metals move gradually through currents, sediment, and water masses. Thermohaline circulation transports nutrients over decades or centuries, distributing them across vast distances. These nutrients feed microorganisms, which in turn sustain higher trophic levels. The slow pace stabilizes ecosystems, preventing sudden imbalances in populations or chemical composition. Deep ocean nutrient dynamics illustrate that the rhythm of environmental processes is extended, creating a measured flow of energy and matter that contrasts sharply with the faster, more variable cycles observed at the surface. Ecosystem stability depends on these extended timescales. Long-lived organisms, slow-growing corals, and abyssal fish are adapted to gradual change. Sudden shifts are rare in the deep, and the stability of environmental conditions allows populations to maintain steady growth and reproduction. Food webs are slow but resilient, with energy passing through multiple levels gradually. Even disturbances, such as particle deposition from sinking organic matter or episodic volcanic inputs, are integrated over time, creating a system that reacts with patience rather than urgency. The slow pace ensures that ecosystems do not collapse due to short-term fluctuations, but respond incrementally, demonstrating how time shapes the survival strategies of life in the abyss. Understanding these processes is critical for modeling Earth system feedbacks over decades and centuries. Climate scientists use deep ocean data to predict how carbon storage, nutrient availability, and water movement affect global temperatures and atmospheric composition. The slow response of the deep ocean means that feedback loops often take decades to manifest fully. Ice ages, interglacial periods, and long-term warming events leave traces in sediments, currents, and chemical gradients. By studying these records, researchers can anticipate future trends, recognizing that immediate surface observations only tell part of the story. The deep ocean acts as a slow regulator, extending the temporal horizon of Earth system dynamics far beyond daily or annual cycles. Cross-disciplinary insights emerge from studying deep ocean time. Oceanographers analyze currents, temperature, and salinity to understand water movement. Physicists explore how pressure, gravity, and density affect the rate of processes and even the passage of time itself. Biologists examine the slow rhythms of growth, metabolism, and reproduction in deep-sea organisms. Chemists study nutrient cycling and carbon sequestration in sediments. Together, these disciplines reveal a unified picture of a system governed by extended temporal scales, where physical, chemical, and biological processes are synchronized to a patient, slow-moving rhythm. Insights from one field inform another, creating a comprehensive understanding of deep ocean dynamics and their influence on the planet. The scientific significance of understanding deep ocean time is far-reaching. Accurate climate models require knowledge of how carbon is stored, released, and transported over long periods. Predicting nutrient cycles and ecosystem resilience depends on recognizing the extended pace of deep water processes. Even fundamental physics, such as gravitational time dilation and signal propagation, can be observed in this environment, offering a natural laboratory for testing theories under extreme conditions. Each observation, from sediment accumulation to microbial activity, contributes to a clearer understanding of the Earth system as a whole, showing how slow processes influence global patterns over centuries. Carbon sequestration in the deep ocean operates on both local and global scales. Organic material sinks slowly, and microbial decomposition is limited by temperature and pressure. Some carbon is buried in sediments, while other portions are gradually transported by currents across ocean basins. The result is a long-term balancing mechanism for atmospheric carbon levels. The slow pace also means that sudden human emissions of carbon cannot be immediately offset, emphasizing the importance of understanding the deep ocean's role in climate regulation. The patient storage of carbon in abyssal layers demonstrates how temporal extension shapes planetary processes, linking physical depth with ecological and atmospheric outcomes. Nutrient redistribution is similarly governed by time. Thermohaline circulation, driven by temperature and salinity gradients, moves nutrients slowly through the global ocean. Surface productivity depends on the eventual upwelling of these nutrients, which may take decades or centuries to return to the euphotic zone. Microorganisms exploit these resources at rates adapted to the slow flow of energy, ensuring continuity in ecosystems. Biological feedbacks, such as nutrient uptake and decomposition, reinforce the extended timing of ecological cycles. Life in the deep ocean is thus synchronized with the slow movement of matter, reinforcing the connection between environmental pace and biological response. Ecosystem resilience is a product of time as much as of structure, Slow growth and long lifespans allow populations to withstand occasional disturbances. Sediment deposition, current shifts, and periodic chemical influxes occur gradually, giving ecosystems time to adjust. Food webs, though slow, maintain balance because each link operates according to extended temporal rules. Predators, prey, and microbial communities all integrate signals from the environment, responding over days, months, or even years. The stability of these systems demonstrates that the slow passage of time is essential for maintaining ecological equilibrium in the deep ocean. Feedback mechanisms in the Earth system often depend on these temporal extensions. Carbon released from surface waters may take centuries to reach deep layers, delaying its impact on global climate. Nutrient cycles unfold slowly, moderating productivity and energy transfer between ecosystems. The deep ocean thus acts as a stabilizer, absorbing shocks and redistributing resources over long periods. Understanding these processes allows scientists to predict how changes in one part of the system will propagate through the planet, highlighting the relevance of deep ocean time for global climate models and long-term ecological forecasting. Cross-disciplinary studies reinforce the importance of extended temporal scales. Oceanographers track water mass movement and mixing rates. Physicists measure the effect of pressure and gravity on processes and even on atomic clocks. Biologists observe slow growth, reproduction, and energy use in deep-sea organisms. Chemists analyze nutrient transformation and carbon sequestration. Integrating these observations shows that the passage of time in the abyss is a fundamental aspect of planetary function, influencing climate, ecosystem stability, and physical processes simultaneously. Each field confirms that time in the deep ocean is both measurable and impactful, extending beyond human scales. Scientific modeling of future Earth scenarios relies on these insights. Accurate predictions of climate change, ocean productivity, and carbon cycling require incorporating the slow dynamics of the deep ocean. Short-term observations at the surface cannot capture the delayed effects of deep water processes. By understanding how time operates differently at depth, researchers can account for the extended influence of the abyss on global systems. This knowledge informs policy, conservation strategies, and climate adaptation measures, illustrating the practical significance of understanding temporal dynamics in the ocean's depths. The deep ocean's slow processes also highlight the difference between human perception of time and natural time. While surface events unfold quickly, the abyss operates on scales that span decades, centuries, and millennia. Carbon moves gradually, nutrients cycle slowly, and ecosystems respond incrementally. Physical signals, such as sound propagation and temperature shifts, are extended across time. Life adapts to these rhythms, growing, feeding, and reproducing, according to patient cues. Human instruments, carefully calibrated and continuously monitored, reveal these slow changes, confirming that the deep ocean is a natural chronometer, recording and regulating planetary processes over long time spans. Ultimately, the slowed processes of the deep ocean shape the stability and resilience of Earth systems. Carbon storage, nutrient cycles, and biological rhythms all operate on extended temporal scales, creating a buffer against sudden changes. Understanding these dynamics provides critical insight into the planet's climate, ecology, and physical processes. The deep ocean is not only a repository of matter and energy, but also a regulator of time itself, influencing how processes unfold over decades and centuries. Its patient rhythms underscore the importance of incorporating long-term temporal perspectives into our understanding of Earth and its future. By integrating findings across oceanography, biology, chemistry, and physics, scientists gain a unified understanding of how time at depth affects global systems. Each measurement, from carbon flux to nutrient transport, highlights the slow yet powerful influence of the abyss. Life, chemical cycles, and physical processes are all synchronized to this extended temporal framework, revealing a world in which the passage of time is as fundamental as the flow of water or the movement of particles. Understanding deep ocean time is essential for modeling future Earth scenarios, predicting ecosystem responses, and anticipating climate feedbacks over long periods. The patient pace of the abyss demonstrates that time itself is a critical variable in the stability and function of the planet. The deep ocean serves as a natural laboratory for extreme physics. Pressures increase by hundreds of times compared to the surface, temperatures drop to near freezing, and light is almost entirely absent. In this environment, physical laws manifest in ways that are both subtle and measurable. Instruments such as atomic clocks reveal tiny differences in the passage of time caused by gravity and depth. Mechanical and chemical processes slow, offering an opportunity to observe phenomena over extended scales that are difficult to replicate on the surface. Just as scientists use satellites and orbiting laboratories to study gravity and time dilation, the ocean's depths provide a stationary, high-pressure counterpart, where the interplay of mass, motion, and temporal flow can be observed in situ. Analogies to space-time experiments become clear when considering the effects of gravity and pressure. Time is not constant in the universe, and in the deep ocean, gravitational time dilation is measurable, though minute. Atomic clocks deployed on the seafloor run slightly faster than those at the surface. While the difference is infinitesimal, it confirms that mass and distance influence the flow of time. This mirrors experiments near massive objects or in orbit, where variations in gravitational potential lead to observable temporal differences. The deep ocean allows these principles to be tested in a naturally occurring laboratory, using conditions that are extreme yet stable, demonstrating that time's passage is not uniform across all environments on Earth. The interconnectedness of physics, biology, and Earth systems becomes evident in these observations. Slowed chemical reactions, extended nutrient cycles, and long-lived organisms all reflect the influence of physical conditions on biological and ecological processes. The behavior of currents, the accumulation of sediments, and the movement of sound waves are governed by physics, yet they in turn shape the life that exists in the abyss. Each element of the deep ocean interacts with the others, creating a coherent system in which time affects matter, energy, and life simultaneously. Observations at depth reveal that time is not an abstract measure, but a real, functional dimension that links processes across disciplines. Human perception contrasts sharply with these slow processes. On the surface, events occur quickly, and our senses are adapted to rapid changes in light, sound, and motion. In the deep ocean, by contrast, physical cues arrive slowly, biological processes unfold incrementally, and environmental changes are gradual. Movements that seem ordinary at the surface take longer to complete at depth. Signals, whether from sonar, chemical diffusion, or bioluminescence, reach their targets with delays, requiring patience and careful interpretation. Time in the abyss is extended, and human observers must adjust their expectations to match this deliberate pace. The contrast highlights how perception is tied to environment and how the deep ocean expands the temporal horizon of experience. The ocean also serves as a mirror for understanding larger-scale Earth systems. Processes that occur over centuries or millennia carbon sequestration, nutrient cycling, sediment accumulation, demonstrate that the planet operates on timescales far beyond human observation. By studying these slow processes, scientists gain insight into feedback loops and planetary rhythms that are otherwise hidden. The deep ocean teaches that change does not always occur in rapid bursts, but can be measured, persistent, and cumulative. Every observation reinforces the idea that the planet is a patient system, and that time itself is a dimension that stretches and folds according to environmental conditions. Observing life in the deep reinforces this perspective. Many organisms grow slowly, reproduce infrequently, and operate on energy budgets that match the slow movement of their environment. Giant tube worms, abyssal fish, and corals all integrate signals over long periods, adjusting behavior and physiology to the extended pace of the ocean. Microbial communities metabolize chemicals gradually, contributing to nutrient cycling and energy transfer at rates far slower than in surface systems. These biological rhythms are aligned with the slow environmental cues, showing that the passage of time is both a physical and ecological dimension. Life in the abyss moves to the rhythm of delayed signals, prolonged reactions, and patient processes. Even human instruments reflect the ocean's extended temporal scale. Atomica, clocks, long-term sensors, and autonomous probes capture small variations in time and environmental conditions, providing data that spans weeks, months, and years. Delays in mechanical response, slow propagation of sound, and gradual chemical transformations emphasize the deliberate pace of the deep ocean. Researchers observing these systems must also operate patiently, synchronizing data collection, analysis, and interpretation to match the slow unfolding of natural processes. Time in this context becomes a tangible factor, shaping both observation and the dynamics of life and matter. The deep ocean's patient rhythm has analogies beyond Earth. Just as gravitational fields near massive objects bend space and time, the ocean's mass, pressure, and density influence the movement of particles, signals, and processes. Currents stretch over decades, sediments accumulate over millennia, and chemical reactions proceed at slowed rates. Observing these effects allows scientists to study time as a variable, understanding how the physical environment modulates biological and chemical behavior. The abyss is therefore not only a natural archive of Earth's past, but also a living experiment in the flow of time, revealing principles that connect physics, biology, and planetary systems. The deep ocean, in its darkness and pressure, operates almost as a timeless system. Events unfold slowly, imperceptibly, yet with measurable regularity. Currents carry energy and nutrients over centuries. Sediments capture carbon and environmental signals over millennia. Organisms grow and interact on a scale defined by patience. Instruments record minute temporal variations that confirm the subtle influence of physical laws on the passage of time. In this way, the abyss demonstrates that time is not an abstract measurement, but a tangible, functional aspect of the environment, shaping processes from molecules to entire ecosystems. In reflecting on these observations, it becomes clear that human perception is limited by our adaptation to the faster pace of the surface world. The deep ocean expands our understanding of time, showing that processes we consider slow are, in the abyss, natural and immediate. The interplay of physics, biology, and Earth systems is revealed most clearly in this extreme environment. Time moves differently here, and observing these differences allows us to see the ocean as a patient, enduring system in which processes unfold with deliberate continuity, unaffected by the urgency of surface events. Ultimately, the deep ocean teaches a broader perspective on the passage of time. From atomic clocks to thermohaline currents, from slow-growing organisms to chemical transformations, every element of the abyss operates on an extended temporal scale. Life and matter respond to subtle, delayed signals. Human exploration and measurement must adapt to this patient rhythm. The ocean records its history continuously, preserving evidence of centuries of environmental change, while simultaneously demonstrating the slow unfolding of energy, matter, and time. It is a laboratory, a repository, and a mirror of natural processes, revealing how time flows differently beneath the surface, quietly, steadily, and with enduring continuity. In the end, the deep ocean is both timeless and deeply temporal. It shows that the pace of the world beneath the waves is measured and extended, where every signal, reaction, and life cycle reflects the slow, deliberate rhythm of the environment. Observing, recording, and interpreting these processes allows humans to appreciate the subtle, patient flow of time in the abyss. The ocean's quiet persistence provides a closing lesson. Beneath the surface, time moves in its own deliberate manner, revealing the hidden, gradual, and enduring forces that shape life, matter, and the planet itself.